Hi, my name is Jim, and this is Pulse Circuits Part 2. And what we're going to start with is charging and discharging when the capacitor voltage, the initial capacitor voltage, is something other than 0. And that's very well could be the case. It's not unusual for it to be something other than 0. And one simple way we could do that would be take this waveform, and notice that we're dealing with a bipolar waveform here. It goes from +5 down to -5, and if we wanted to find some point, is we could simply shift this up by 5 volts, where we would be dealing with 0 and 10 volts, do the math to find out whatever VC is at a certain time period, and then subtract 5 volts from that, which would give us the correct answer. However, there are more robust equations available that allow us to do the same thing. Now, in the first part, we were looking at two different equations. One was a charging equation, which had the quantity 1 minus E raised to the -T over RC, and then we had the discharging equation, which was basically Vs times E raised to the -T over RC. We could use this equation instead of those other two if we so chose. All that would change is our final voltage, that's where we're going to, and our initial voltage is where we're coming from. So this is a very general equation, and we're going to start out here. Again, we're going to do this in pieces and look at number 1, and then we're going to be looking at number 2. So for number 1 here, our V initial is going to be -5 volts, and what we see in green, and I guess I forgot to put this in here, is that that goes from -5 volts to +5 volts, is our starting point here. Our VC is going to be, voltage across capacitor is going to be -5 volts, and that's because this point is kind of like the end of this point. So this is where we're starting out. And our final voltage, what we're charging to, is going to be 5 volts, and once again, for this to work, our time constant has to be, our 5 time constants has to be greater than the period divided by 2. And the reason that is so that we can reach at 5 time constants basically the final voltage. So this is where we're going to start here. The capacitor voltage is going to be equal to V final, and I'll be using VF from now on. And for number 1, V final is going to be 5 volts, +5 volts. That's where we're going to be going to. And V initial is -5 volts, which is where we're coming from. And then we have the standard E raised to the -T over RC, or if we like, -T over tau. Same thing. So what we want to do with this, for an example, is to find the capacitor voltage at 3 milliseconds, and we're going to be starting out here at a -5 volts for the initial value of the capacitor voltage. So populating the equation, we have VC equals 5 volts, which is going to be V final, this guy, plus the quantity V initial, him, -5 volts, minus V final, which is +5 volts, and I'm explicitly putting the signs in here so as not to be confused. So this plus sign is called a unary operator. It's telling us the sign of 5 volts. This negative sign is a unary operator, which means it's only working on one term. It's telling us the sign of this voltage, and this is a subtract. That's a binary operator. It's sitting between two terms, so that's an action to be done. So if we figure this out and do the parentheses first, is what we get is -10 volts, -5 minus a +5 is going to give us -10 volts. And then if we take our natural number E and raise that to the -3 milliseconds divided by our time constant, which for all of our examples here is 2.2 milliseconds, is what we get from this is 0.256. Next, what we have to do is, by the order of operations, do the multiply before the addition, and that'll give us 5 volts plus a negative 2.56 volts, and that gives us an answer of 2.44 volts. So if we want to find our final voltage at 3 milliseconds, starting here, it'll be a positive 2.44 volts. Now, it's obvious that you need to keep careful track of your signs. So doing things like this here doesn't hurt. Anything that avoids a simple mistake is a good thing to do. So if we look at that here, at 3 milliseconds, and this would be 2.2 milliseconds, it's one time constant, two time constants, and so forth. So 3 milliseconds would be about here, and I call that point A, and that would be our 2.44 volts. Next example is we're going to find the capacitor voltage at 0.5 milliseconds, and again, this is in grouping A. So we'll just kind of use what we already derived on this side. Our final voltage is going to be plus 5 volts. The component inside the parentheses here is going to be negative 10 volts. And now what I do is raise e to the negative 0.5 milliseconds divided by the time constant, which is 2.2 milliseconds. And that gives us 5 volts plus a negative 10 volts times 0.796. So that's going to be e raised to this value here. Doing the multiply operation first and then adding in 5 volts, so multiply operation will give us a negative 7.96 volts. And then by the order of operations, we're going to add 5 volts to that, which gives us negative 2.96 volts. So at time equals 0.5 milliseconds, starting from an initial value VC of negative 5 volts, we end up, and this is about 0.5 milliseconds here, at negative 2.96 volts. So we can see that this general equation here works pretty well. And let's go on and look at this at number 2, and we'll do an example there. So number 2, V initial now is plus 5 volts, and that is because we're kicking off right here at the beginning of our second, I don't want to call it period, our second T over 2, I suppose would be good. And our final voltage is going to be negative 5 volts. So we can't switch around these values in the equations, and what our desire is to find the capacitor voltage at 2.5 milliseconds, and that is relative to number 2. So this is going to be our starting point right here, and we want to go 2.5 milliseconds into that. So this is our general equation here, as we've seen before, and now we're going to populate it. And our final voltage is going to be negative 5 volts, and we're going to add to that the initial voltage, which is plus 5 volts, minus the final voltage, which is negative 5 volts. So we're subtracting a negative 5 from a plus 5, and what that gives us is a plus 10 volts. Next, we're taking E and raising it to the 2.5 milliseconds divided by one time constant, which is 2.2 milliseconds, and that ends up giving us a value of 0.320 times 10 volts, order of operations. And then we're going to add that to negative 5 volts, and we do the math on this guy. For the 10 volts times 0.320, we end up with a value of 3.20 volts. Added to negative 5 gives us negative 1.79. So at the time of 2.5 milliseconds, I say millivolts? Okay, milliseconds, relative to the beginning here, we see that we're down here, and this would be 3 milliseconds, at negative 1.79 volts. So this would be charging starting out at plus 5 volts with a terminal voltage of negative 5 volts. Now let's look at one other thing here. To find the current, and I'm not going to get into a lot of detail, all we need to do is find the capacitor voltage. And what we know about that is if we subtract the capacitor voltage from Vs, whatever it is, and divide that by R, we're going to get our current. So basically, in general, the current flowing in the circuit, I, would be equal to the source voltage, and in this example, that can be either plus 5 or minus 5, depending upon where we're working. Subtract from it the capacitor voltage and divide it by the resistance, and that'll give us the current flow. And we have to be very careful of polarity here. And the current is defined as flowing in this direction. Who defined it? I did. Does it have to be defined that way? No. But if the physical current flows in the other direction, it's going to be a negative quantity. That's the whole point of it. Okay, here, so if we take a look at the current, and this is from the previous circuit, what we see is that the input waveform, the driving pulse, the source voltage, is going from negative 5 volts to 10 volts, and when we do that, the voltage across the capacitor is basically going to be 10 volts, which means that the current flowing in the circuit now is going to be determined by the source voltage minus the capacitor voltage. So if we look at this in detail, if we're starting from this point, VC is negative 5 volts because that's what it's been charged to over here on my left. So let me just put negative 5 volts here, plus and minus. And now the source goes from negative 5 volts up to positive 5 volts. So what we have is this guy. Minus and plus means that the source voltage is series aiding with the capacitor voltage, giving us 10 volts actually at T0 plus, just for that instant when it changes. Now you need to see that these are series aiding at this point, and if you get that, then the current flow is going to be easy. We have, in fact, 10 volts now, 5 volts here and 5 volts here, across the resistor, so 10 volts is going to give us 10 milliamperes. And that 10 milliamperes is going to exponentially decay, and at 5 time constants later, that's 1 tau, I overwrote it, 11 milliseconds, is it's essentially going to be 0. And then things switch around. The capacitor voltage now is going to be at plus 5, so I'll use a different color here, plus and minus, and this is going to change from minus to plus, and once again is we're series aiding, and we have negative 10 volts in the circuit, and the current is going to be flowing in the opposite direction, plus to minus, and this is going to drop down to negative 10 milliamperes. And this is, at this point, just remember that the capacitor now is charged to plus 5 volts. So our current now is going to drop down to negative 10 milliamperes and then exponentially decay back to 0. So what this kind of emphasizes at the transitions is the importance of adding voltages and understanding what's series aiding and series opposing. And that's the only way we're going to get correct answers when we look for current here. Now, if we get this wrong at a transition, the current's going to be 0. Obviously not correct. So that would be the current flowing from the previous circuit. And we need to summarize a little bit. So what does this mean? And I want to give you 2 examples here. I always hated learning things when I didn't know what good they were to learn them. And in audio testing, many times, say a amplifier that you bought, 50, 100 watts, paid a lot of money for it, and you apply a square wave to it, there's certain things that you don't want to see. Now, right here, what I'm showing, and this is dependent upon the frequency that you're putting into it, and in a later course you'll learn exactly what an edge means in a pulse, because a pulse is made up of many frequencies. Is that if we see this here rounding off, is what we basically have is a charging capacitor. Now the meaning of that in an audio circuit is that some high frequencies are being attenuated. That may be good, it may be bad, it depends upon the frequency of our driving pulse. So that's good to know. And in a triac circuit, like a light dimmer, we trigger the triac at certain periods of time relative to 60 Hertz, and that turns on the triac and turns on the light at different times. Now what's important in a triac, which is a AC control device, it's kind of like a transistor in general terms, is that we turn it on hard and fast. So this would be the pulse that's applied to the gate. And this is like getting punched in the face. It's a lot of energy delivered into the triac, so it turns on now. But if we take this spike and spread it out on a scope, and that would be with the time base, is what we'd see is that it's actually a decaying exponential. Now, if I showed you the circuit that's driving the triac, is what you would see is an R and a C that's coupled into a special device called a diac, which is going to dump C into the triac's gate. And it actually looks like a decaying exponential when you span out your scope display. So there's a lot of practical applications in this that that you're going to come across. Let me put down one other, since I'm thinking about it, is if we have a low frequency square wave, say 50 Hertz, and we're viewing this on a scope, and the scope is set to DC, and what DC means is direct couple. 3 different definitions of DC: direct current, direct couple, and duty cycle. And if we were to flip that on AC coupling, is what that means is that the scope is going to put a capacitor in series with its internal impedance. So it's going to flip these 2 parts around, and then what we would be seeing here is something which would look like this. So what that's saying is that the R and the C that's associated with this are discriminating against low frequency components in the signal. So this pulse stuff and what we're learning about this occur everywhere, and if you're not aware of this, you can draw some very wrong conclusions from a pulse waveform. Alright, last thing we want to do is, given a capacitor voltage, is find T. So what we're going to do is say, okay, if I let VC equal 3 volts, what is the time? When does that occur? And again, we're going to, this be 5 tau or 11 milliseconds, and the time constant of our circuit is still 2.2 milliseconds. So in this case we have a unipolar, I'm trying to make this a little bit simpler, pulse, meaning it's only going to go in one direction, and I'm telling you that VC initial is going to be 0 volts. So what we're going to do is solve this symbolically first, and then on the next page we'll put numbers in it. And solving it symbolically is, I think, more challenging because you can't combine things like you can with numbers, because you don't really know what the values are, so you have to keep them as a symbol. So this is our starting equation. VC equals our source voltage times 1 minus the quantity negative T over RC. So that's our charging waveform. And what we want to do is isolate the time. Now there's a problem with that because this is sitting in the exponent of a natural number. It's a power, and we have to figure out a way to get it out. So first thing we're going to do is get VS out of the way, and we're going to move him over to the other side by dividing both sides by VS. And what that'll give us is it's going to have the capacitor voltage divided by VS. And when you see this, what you have to kind of think about is this at the maximum can be 1.0 or less with a minimum of 0 equals 1 minus e raised to the negative t over RC. So I've taken the parentheses away from this now. I no longer need them. And our next step will be get rid of the constant 1. So what I'll do is subtract 1 from both sides, giving our capacitor voltage divided by the source voltage minus 1 equals negative t to the e raised to the negative t over RC. Now, if you remember the other sheet where I drew e to the negative x and e to the x, is we were always above the abscissa, the x-axis. In both cases, at no time did we go negative on the x-axis in the quadrants 3 and 4. So the opposite operation of e raised to a power is going to be the natural log ln. And because e to the x or e to the negative x is not defined as a negative number, if we try to take the natural log of it, which is the inverse operation, our calculator should complain. And if you do that, take the ln, say a negative 1, and you don't get a nasty message, you need to buy a new calculator. So what we have to be very careful when we do this is we don't end up in a situation like that. It's usually easy to change by multiplying both sides by negative 1, because that doesn't affect the balance that needs to be on both sides of the equal sign. So what I want to do at this point is to get rid of the e, and I'm going to do this very verbosely, step by step. I'm going to be taking the natural log of this side and the natural log of this side, and the way this would usually be written is this wouldn't be here, and you'd end up with negative t over RC. So what we want to do here is, since we got a negative here, is multiply both sides by negative 1. And if we do that, what we see is we have the natural log of negative VC over VS plus 1 and the log of a positive e. And I might be looking at this saying, well, wait a minute, something's not right here. But remember, this term is going to be 1 or less. And now we're adding this to a positive 1. So inside the parentheses, the worst case we're going to have is 0. Other than that, it's going to be a positive number. So we have the natural log of this quantity, and since we did this, essentially taking the inverse operations gets rid of the e, we end up with this is equal to negative t over RC. So we're really close to solving this now. All we have to do is get t by itself, and we'll do that by multiplying both sides of the equation by RC. So in switching sides here, we end up with negative t equals the product of the time constant RC times the natural log of VC, negative VC over VS plus 1. So negative t isn't exactly what we want. So guess what? We have to multiply by negative 1 again. And in so doing, we get a positive t equals negative RC times the ln of this guy. And if we were to substitute in our values here for our circuit values, is what we would end up with is t equals 2.01 microseconds. So substituting in values simply means that we have VC, which is 3 volts, and VS, which is 5 volts, and the time constant is set at 2.2 milliseconds. By the physics of it, we chose the capacitor and the resistor, and we get this here value, t equals 2.01 milliseconds. And I kind of want to check this. Work through all these numbers and stuff. It's good to check things. So what I'm going to do is substitute the t I got into the equation, solve for VC, and if everything goes well, it ought to come out to be 3 volts. So in doing that, standard formula here that we've been using a while, and doing the math on this, as my calculator pulls up a 2.994 volts, which good enough, 3 volts. So I'm fairly confident that the solution to the problem of finding t would then be this here equation symbolically. Now, let's do the same thing with numbers, and this should be, I think, a little bit more comfortable because we can combine things. So here's our starting equation for the charging exponential, and we're going to start by isolating t again. So we want to get rid of our Vs here, which is a multiplier or source voltage, which is 5 volts. So I'll start by dividing both sides by 5, which gives me here 0.6 volts, stripping the parentheses 1 minus e raised to the negative t over the time constant. So that's a good start. So I want to get rid of the constant, and then what I'm going to do is subtract 1 from both sides, which gives 0.6 minus 1 equals a negative e raised to the negative t over 2.2 milliseconds. Combining these here is I have 0.6 minus 1 is going to give me negative 0.4 is equal to negative e raised to. So I want to kind of convert this. I need to convert it. So I'm going to multiply both sides by negative 1 again. So I end up with positive 0.4 equals positive e raised to the negative t over our time constant. And then, since I want to isolate t, I'm going to take the natural log of both sides, again verbosely written to show the operation here, and that will isolate the ln of natural log of 0.4 is negative 0.916 equals t over our time constant 2.22 microseconds. And getting rid of the negatives again, multiplying by negative 1, we end up with a positive 0.916 equals t, it's now positive, over 2.2 milliseconds, our time constant. So we're getting there. Let's see, now all we have to do to isolate t is multiply both sides by 2.2 milliseconds, and showing that here, and then multiplying them together gives us 2.01 milliseconds, and that will be the time that we wanted to find before, same as the answer here. So doing it with numbers is a little bit easier, I think, because like at this point we can actually combine these and come up with 0.6. So this isn't difficult, I don't think. Once you know the equations and once you're comfortable with working with the natural number e raised to a power and its inverse operation, which is the natural log. And these are probably going to be the most different things having to do with pulse circuits that you've seen so far. So that should do it for part 2, and thank you for watching.